Yeah. Okay, now everybody here should turn off deafen your audio. Anybody else? So this is kind of like you need to. I think if you just deafen there, then it should be no output from this one. So now we have almost the full Hollywood studio set up here. I should have asked Sean to help me with this. Okay, good. So let's get started today. I want to do some background theory first, a couple of nice experiments with vision processing, and then we're going to look at doing some programming. And I shall record this. And so the class will be recorded today, just so that everybody knows, so watch your language. And first slides are going to be about blue blindness. Let me just try and take a picture of that. Share that in case we need a picture later on. So let's just take an image and then do some simple processing with it, in particular reading the image. So the image that I have right now, copy image. What is that?
Third one.
Third one? Uh, Switch to the other. Okay, so here's just a picture that I took just now. And here's our change the image here. So we start out by loading some commonly used libraries, matplotlib, pyplot, doing different plots, numpy arrays, and random, and also the OpenCV library, CV2, the latest version. And then we have an image, so first we need to understand how that is represented in the computer. So here we have a very powerful library for various computer vision tasks. So when we process images on the computer, then what we have is a two-dimensional array of what's called picture elements, and those represent the color information or the grayscale information at that particular location in the image. The 2D array is stored in row major order, which means that successive elements are along the column. So the row changes last, the columns changes first. So if you look at the image, and this is your image, then basically the first element in your image is going to be stored here in memory, and then it's going to go along the columns, and then along to the next row, also along the columns, next row along the columns. Now, why is that important? To know which order the pixels are represented. That comes a little bit later. We're not there yet. Right? Even if you just read pixel elements now, right? Even if it's just grayscale, and you wouldn't have a problem with color swapping. The main importance is that for efficiency, if you process the image along the columns, the way that it's stored in memory, versus, so that would be left to right. So you start here, for example, and you go along the row. Or you start here and you go along the row. Right? Increasing the columns or decreasing the columns. Then, as opposed to going up and down. I mean, I could just start the image here and start processing it going downwards. Right? Or upwards along the rows. Then what impact will that have on runtime? And why? Which program will run faster? As a rule of thumb, if you follow along the columns here, if you process your image one row at a time, you will have and you make no other changes apart from going along up and down the columns, then your program will run about 10 times faster just moving along the columns as opposed to the rows. So you always want to process the image, if you can, you always want to process the image going this way. And the reason for that is because when your processor accesses a single pixel here, let's say I'm looking at this particular pixel here, I read that into memory, then what will actually happen? Then your CPU is going to access this block of memory, but main memory is about 1,000 times slower than your CPU register access. So reading a byte out of memory is a very expensive operation for the CPU. So that's why, in order to overcome this problem, in order to overcome this bottleneck, the modern CPUs have a very elaborate cache architecture, right? So you have heard of level 2 cache, level 1 cache, level 3 cache on a i7, i9. What that means is, when you read a block of memory, actually the CPU assumes that the bytes that are near to it will be useful, will be read next. So all of this data, when you read this pixel here, about, depending on the power of your CPU, about 64 kilobytes are going to be read in at the same time. So if you access the next byte over, that is already in the cache, so that will be accessed extremely quickly. And the next one, next one, next one, next one. If I access the pixel below, then that's actually quite far away. So all of these bytes are not going to be processed, and it won't be in the cache memory. So then it'll read this entire row into cache memory and allows you to process it, and so on and so forth. So if I go along the rows, then I actually make very good use of my cache memory. So that means the cache affinity of that particular algorithm is very high. If you go along the columns, your cache affinity is very low. And as you read in more data into your cache, cache memory is very expensive, so it's very small. It's like a couple of megabytes. So once it's full, the CPU is going to throw away the data. So if you have a large image and you start processing here, you're going to get the whole row, then you process the next row, that's in cache, that's in cache, that's in cache. Now your cache is full, so it's going to throw away some data. So when the CPU wants to throw away data, what strategy does it usually use? There's different variations by different CPUs, but in general, it's the idea of a least recently used strategy. So things that it just accessed, it will try and keep in cache. Data that was accessed a while ago, that is stale data, is assumed to be stale data, so that will be expunged from the cache. So you read a row, you process one pixel. You read the next row, you process one pixel. You read the next row, you process one pixel. Next row, now your cache is full. That row most likely will be thrown out of the cache. Then you start reading. When you go back to this pixel now, that memory is not in cache anymore, so it will be loaded from main memory again. So that will absolutely kill your performance by at least a factor of 10. Just using the wrong order in which you process your image. If you really must process an image based on the columns, then it's actually much cheaper, much faster to take the image, rotate it by 90 degrees, run your algorithm, and then rotate the resulting image back by 90 degrees. Because that you can also do, you need to use some extra memory, right, to do the copy of the image. But you can do that also using row major order, so that can be done much faster than any kind of column-based ordering. If you have to do some more elaborate processing on images, then sometimes programs actually, let's say I want to do some very complicated processing, a morphology operator, for example, like open and close, which runs over a certain area. It is actually beneficial for the way that this is usually processed then in a graphics program like Photoshop. Photoshop does that, or GIMP, or Krita, any kind of programs that have complex filters. They actually take a block of the image that is, and the size that they take is specifically targeted at the size of your cache. So they check the CPU, they check how much cache memory is available, then they copy a 64 by 64 pixel block, copy it into memory, process it all in there in one cache access, then copy it back, and then they go to the next block, the next block, the next block. So for extremely time-sensitive algorithms where you need to look at areas and process them repeatedly, then that's what you have to input. But In general, never any two-dimensional array is stored in row major order, so never process them along the columns. Always process them along the rows. Unless you want your CPU to generate a lot of heat and run very slowly. Now, the most common format for pixel is the RGB format. It's an additive color model where we have 3 channels: red, green, and blue, the 3 primary colors for addition. The data in each channel is 8 bits. So we have from 0 to 255 different levels for red, for green, and blue. So in total, our image, each pixel is going to be 24 bits. Sometimes we also have ARGB format, where A stands for the alpha channel. That's usually used in graphics programs, where you want to have colors that are transparent, so things are looking through. In computer vision, that's usually not the case, right? Our cameras don't understand transparency of objects. But especially if you work with embedded systems, it's actually quite nice to use this particular format, because a lot of the lower level CPUs, like the low ARM cores, ARM 7, ARM 9, things like that, they actually can access 32 bits if it's aligned on a word boundary much faster than if it's not aligned. So if you have multiple of 32 bits, multiple of 4 bytes, then the CPU can access that faster than if you have it aligned at 3 bytes. So that's one advantage. And the other thing is that I kind of like it because when you request an ARGB frame from your camera, the camera doesn't have any transparency, so it usually just sets that alpha channel to 0, right? Which means opaque, like no transparency. So, but often when you do processing on an image, lower level processing, then you would like to do things like mark this pixel. I've seen this pixel already. If you do a flood fill, you need to mark every pixel on whether you've processed it already, right? Or if you do convex hull, finding convex hulls, finding regions, you want to add an ID for the region and then merge different rows together fast. And there, this extra byte here is kind of nice because you can just use that to put in a 1 if you processed the pixel before. Or 1 if it belongs to the ball, 2 if it belongs to the goalposts, 3 if it's part of the vest on the robot, something like that. Then you don't need to store that information separately. There's also many different other kinds of color formats, and in today's class we basically want to sort of just try some experiments with color and the way that the human visual system can perceive color. But one that is also popular is RGB 565, which is a 16-bit format where the red channel is 5 bits, the green channel is 6 bits, and the blue channel is 5 bits. And that color format is also it's smaller, so the CPU can usually process it faster because it needs to access less memory. It's 33% smaller than the 24-bit color format. And the problem with it is that in order to read the red, the green, and the blue values, you need to take the 16-bit value and then do a couple of hands and shifts in order to extract the red, green, and blue values. The advantage of that color format is that often you would like to have, you want to detect the ball, or you want to detect the wall, or you want to detect some colored object, then you need to define a procedure, some predicate, that tells you true or false. This belongs to the ball color or is not part of the ball color, right? So that's some function that returns the way you pass in a pixel, and it returns true or false based on this is orange for the ball, or this is if you need to implement an algorithm for counting cookies. Some company in Taiwan produces cookies, so you need to write a vision system to count how many cookies come down the conveyor belt, right? The cookies are all in a blue package, then okay, you just need to count the number of blue blobs that are running down the conveyor belt. That's a pretty simple task to do. And then the most straightforward approach, as you can probably imagine, is that you set thresholds. So you say, for this to be part of the cookie package, the red channel must be between 100 and 200, and the green channel must be, so you have a minimum threshold and a maximum threshold for red, green, and blue. And then you can do some other things with the color. There's some more elaborate color methods, color predicates that people have worked on, and I'll talk a little bit more about that in a little bit later in the class. But the one nice thing about RGB 565 is that the color predicate can become pretty complicated. Some of them were calculating cosines, converting the RGB vector into polar coordinates and things like that. Mapping to HSV is also a non-trivial operation, right? That may take some time. The nice thing about RGB 565 is that it's a 16-bit value format, so what you can do is, instead of having a algorithm, you can just do a lookup, because if you have a 16-bit is 64 kilobytes, right? Actually, 16-bit is 64 kilobytes, yes. So that means that if you have 64 kilobytes table with just one byte, you can just put in 1, this belongs to the ball, 2, this belongs to the wall, this is color blue, this is color red, basically, right? So then you can have the most complex function you want, you can just calculate that for 64 kilobytes. For 24 bits, your table would be 2 to the 10 is 1 million, 2 million, 2 to the 20 is 1 million, so then 21 is 2 million, 22 is 4 million, 8 million, so 8 megabytes. You would need 8 megabytes, so then that's a pretty big table. Also, indexing it into memory would not be so efficient. On a modern workstation, it would not be a problem to have an 8 megabyte table to look up. But usually people then just use the RGB 565 if you do that kind of processing. And when we started working in robotics in mid-1990s, I have to scroll way back in time. Way back. These will be some of the first ones that we did. Here we have a toy car that we bought in the toy shop, a remote control toy car that we connected to the parallel port of a PC. So the car only had left, right, forward, and backwards. So digital controls. Right? You could not turn like 10 degrees, 12 degrees, or something like that. And so it was a pretty crappy toy car. But my point was that if you give that toy car to some children and let them play around with it for a while afterwards, it can do a pretty good job driving a racetrack or doing various tasks. And my goal was to be able to do that as well as children would be able to do. And now here, we have a global vision system. So it's a camera looking at the playing field from the side. So basically, like you would be looking at the playing field, what you will be seeing. Basically, this kind of point of view. And then there's yellow dots on the playing field. And the task was for the robot to drive on top of the yellow dot and then sit there for 3 seconds and then go to the next yellow dot. And so that worked quite well. But this would be an example where you would think that it should be very easy to find the yellow dots, right? Because we have a green playing field, some white walls, and then just the yellow dots to look for. And of course, we also need to find the position of the robot. So you can see here, we just had a blue table tennis ball mounted on top of the robot in order to track the robot, and then it drives from one to the other. So when we did that, we just thought, how hard can it be to find the yellow? How hard can it be? Then it turns out it's actually much harder than you think. And that was then. Nowadays, so when we started this, we basically extracted 24-bit colors from the camera all the time, right? Because we thought, okay, it's not so easy to find the yellow dots, so it's stupid to throw away data, right? So we want to get the best image we can, so we were capturing 24-bit images. After we worked on this for a year or two, we realized that, in fact, any kind of color predicate that you come up with that uses the last 3 bits of your color channel is way too sensitive. So what would happen is, to get something like this to work, this one, or then later on we got better. We have the same thing now with the bridge, so it's 3-dimensional, and then we also can play soccer. So this is where we won the world championship. So at that time I was at the university. And you can see now we have more robots, so not only do we need to find the position and orientation of one robot, but we need to find the position and orientation of 10 robots on the field, or 8 robots, and the ball and the goal, in order to shoot the ball into the goal. And so we have these colored hats with the different IDs and different team markers. Now at that time, when we were working on this, we actually only used the RGB 565 because basically what we realized is that if your color predicate is so sensitive that you use the last 3 bits, it is over specialized, over engineered. Then if somebody opens a curtain, all of a sudden your colors are going to be off because the intensity is different. So in order to get this to work, when we went to the competition, there's at RoboCup 2 days of setup time. So 2 days where there's no competitions, where all the teams just get ready to play, right? And for 2 days, we had one student doing nothing but color calibration all day long, and the other teams the same. And every team hated this guy because basically if the vision doesn't work, then you can't do anything. Like, you can have the best strategy, but if you don't know where your robots are, you're not going to score any goals. If you don't know where the ball is, there's no hope of scoring goals, right? So it was that guy's job to make sure that you can find the ball and find the robots. And everybody hated him because the task was basically impossible, because everybody was using colors and RGB color spaces, and it is very tricky to do that. And then as soon as somebody would turn on the light, all the color calibration was wrong. Then all these guys would rush back to the computers trying to recalibrate. When we had competitions, depending on the referee at that time, how tough he was, teams would always come and say, oh, we're not quite ready yet, we just need to do some color calibration. And then, okay, 5 more minutes. Okay, then half an hour later, are you done yet? Yeah, now we're ready to play. Now the other team says, oh, no. Now the colors changed, so we have to recalibrate. So it was a total nightmare. And nowadays, basically now if we talk with students about approaches for any kind of processing in robotics applications, like for the FIRA, basketball, archery, that kind of thing, our first approach is always to throw away the color and use the shapes first. So we look for circles and things that could be balls. Then we look at the position of objects, whether that makes sense. If I saw the ball previously in this location, then it's okay if he's now at this location. If the ball was here and now it's over there, then something was wrong, right? So then we add low confidence intervals and things like that. And only at the very last instance do we actually check the color and say, okay, you already know it's a ball. I know it's at the position where the ball should be. I'm already 90% sure that this is a ball. I just want to make sure that this could be called orange or red or something. And then at that point, the color predicate is really not that important anymore. And that's why nowadays for the RoboCup competitions, humanoid field, we don't. At the beginning, everything was color coded: orange ball, blue goal, yellow goal, magenta vest, cyan vest for the players. Now ball is white, goal is white, field lines are white, and a green playing field. There's no colors in the environment anymore. Because A, we got better at processing images like that and understanding the world around us, and B, color is really, really hard. Much harder than you think it is. Now there's other color spaces that sometimes you get when you do image processing or computer vision. HSV is a popular one. I'm not going to go into the details of it, but basically it's a color space that is supposed to model more closely how the human visual system works. So it has hue, saturation, and value or lightness for intensity. And so it's not really a cube like the RGB space. It's deformed like that. And then there's different ways that people, psychologists, have worked out what the color differences should be, and a couple of versions of those. On the computer, HSV is pretty popular, or HSL, but in reality, um, it usually is not worth trying. It's usually not worth to convert it to HSV. If your data comes in HSV already, then you process it as an HSV image. If it's an RGB, I would just process it in RGB instead of trying to do various conversions. YUV is a color format that was the first color television used it. It's Y is your intensity, and U is the red and blue component of the signal, basically. And what's interesting about those is that it gets at the fact, the main disadvantage of the RGB color space is that if you look at the mouse here, then what color is the top of the mouse? Red, right? We all agree it's red, right? Is it different reds or just a single color? Different shades of reds or just a single color? I think most people would say it's just a single color, right? But when you actually look at it, then you see that if I take a picture of this, this definitely is not the same pixel values, right? Here, it's much brighter than over there and there, right? So when your eyes look at it, then they actually see that this is not the same red. You realize, when you pay attention, you can detect this, right? You realize very clearly that there's shadow. But when your brain interprets it, it knows it's a mouse. It knows that things are built out of the same component most of the time. It knows that lights will increase the brightness of pixels. And it knows that shadows will decrease the brightness of pixels. So your brain is just going to tell you, yeah, that's the same color. The problem is we have no idea how the brain actually does that. Because of all the possible ways that this object could be constructed, and there's an infinite variety of those, your brain picks the one that makes the most sense. Now, on natural scenes, that works great. The brain does a fantastic job, but if you look at artificial scenes or even natural scenes that are sort of a little bit unusual, then you can easily fool the brain. There is lots of optical illusions that we fall victim to. And what's interesting is that it's basically everybody that this happens to. Right? It's not something that you learned. It's sort of built into your hardware as you open a new tab. Uh, install here. Oh. So if you have a look at this image, right, then what color is square A? Gray. And what color is square B? White. Yes. How many people agree with this? Right? That's what you see. Right? And you guys know this already. Actually, B and A are exactly the same color. Okay. Now, I don't have the program installed to prove that to you, but if I have a color picker and I check this brightness value and I check this brightness value, I guess I just have to install. Okay, I'll just install Krita quickly because that is actually pretty cool. Pretty cool effect. And how do I copy this image?
Yes.
This one? No, I don't know if I can. Fun painting. Insane. How do I open from clipboard? This one? Okay, clipboard. Yes, copy. No, save. Yeah. No, no. Doing now. Come on, come on, come on. I don't know if we can process. So where's This is create, right? And then download something, don't download, no. Okay, so here we have the image, right? And no question to our brain that this is white, this is gray. When I look at it under the color picker, then you can see if I click on here, right, then the brightness value is right in the middle here for the color. These three are aligned, it's on the top left. If I click on here, it's exactly the same color. If I select by color, then this whole area here, that's all one color. And so how does this happen? Select. How does this happen? How does this image fool your brain? It does that, and when we think about it, we think, okay, well, it's because here it casts a shadow, here it casts, it's in the sunlight, it looks like in sunlight, so there's a 3D cylinder there that casts a shadow, so our brain knows about shadows and lights, and so if two pixels are the same color in the shadow and in the sunlight, then it thinks it's brighter in the shadow than it is in the sunlight. The original color without illumination, not taking the illumination into consideration. If it has the same pixel value in here than there, then it should be white in here and dark there in the shadow area. And that, of course, that's a good heuristic to follow. That works in natural scenes, but this scene is not a natural scene. So now we can have a look and see what happens. How can we actually get rid of this particular effect? So most people think that this cylinder here is very important for it. But what I can do is I can actually cut out the cylinder. So I just crop the image. And when I crop the image, then you can see that the effect is maybe a little bit less, but it's still very clear. It still looks like this is white and this is gray. Dark, black and white. So then I can crop it in here a little bit more. I can make it very small. And our brain still thinks, yep, definitely two different colors, black and white. So the cylinder alone doesn't explain this effect. I would argue that probably it has nothing to do with it. You don't really need the cylinder to fool the brain here. So now, how can we tell the brain that it's wrong? So what I can do is, let me select the color. So I take the black color here, and now I just start drawing. So now I'm drawing, nothing happened yet, right? Still white and black. And now watch this. Boom. So now your brain says, no, these are actually the same color. And the only difference is like if I have that line here or not. So I think that is pretty phenomenal what actually happens. Now people have done studies with this and they've looked at the optical nerve, the data that is coming back from your eyes, and the eyes tell the brain, yeah, those two are the same color. Then your brain goes, no, you guys have been lying to me all your life. You're completely useless. I know what this is. This is white, this is dark. And then from then onwards, your brain has no hope to recover from this. Right? You cannot see, even if you know that they are different, even if you know they are the same color, you cannot make them the same color after your brain decides that they're black and white. Right? The only thing you can see there is black and white. So what happens here? Then when I draw the line, why does that allow the brain to switch all of a sudden? Well, it seems to me that the brain has this notion of consistency. So an area that is going along, that is following the same color, right, that is assumed to be the constant color. And that's what's happening here. If these two things are connected and the color doesn't change, then the brain says, oh yeah, absolutely, they are the same color. I said that all along. So, and here, we're not even talking about color, right? This is just black and white. This is just a grayscale image. The green cylinder doesn't really do anything. I'm sure you can make it a red cylinder and it won't change anything on the illusion. So this is a very cool optical illusion. Another one that I like a lot is this one. Now I just have to position it properly. And to switch. This is not going to work for virtual class members, but you can try the same thing. Use your finger. So which square is darker, the top one or the bottom one? Or what color is the top and the bottom of this shape? They're the same, but now it's just because I bring it up on their optical illusions, right? How can I prove that? Pretty easily. It's sort of like magic. I just have to put my hand there, right? So this region here, this is the one that makes that optical illusion work. Right? If I don't have that there, if I have my hand there, then you see it as the same color, correct? So it's like a very easy magic trick. I can change the color of the background. Actually, you can't, but it looks that way. So again, here, we're not even talking about color and color perception. We're only talking about black and white. There's no color associated with it. So color perception is very tricky. It just seems easy because your brain is really, really good at it. So let's have a look and see how we can show some images for the using OpenCV. So that would be CV to IMRead, and then you can just pass in the file name. And here I resize the image width by height just so that it processes a little bit faster on the Google Collaboratory. And then we can also show it in Matplotlib if you want to display an image, just using it like that. So this is the sample image. That I just took. And when you look at that image, then what do you see? Is it correct or not? Where are those blue block boxes? They don't actually exist. If you look at this here, the boxes are not blue, but brown beige. The cardboard boxes there. They don't have this color, right? But they are those boxes. So this is one of the problems that you end up with when processing images. Sometimes you have to be careful. Depending on what endianness your processor has, you may end up swapping the red and the blue channel. That's because some processors store a 32-bit or a 24-bit value with the least significant byte first, like the ARM, and I don't know about the new Apple M1, M2, M3, whether they're little endian or big endian. Does anybody have a new Mac? No? Okay. Intels are usually also little endian. MIPS and Motorola processors used to be big endian. It determines how you take multi-byte values and compound them to mix them into a single multi-byte value, whether the least significant byte is stored first or the most significant byte. If you do that on a 24-bit image and you get it wrong, then the middle, the green channel is not affected, but the red and the blue are going to be swapped. So with OpenCV, you have to usually swap the color channels between what you read in and how it's being processed. And swapping the color channels is actually pretty easy using the NumPy array functions. Why does that swap the color channels, this one line? This is using the NumPy slicing syntax. So I can, if I want to extract an image, for example, I can go from row 450 to row 600, from column 400 to column 600, right? So this colon format allows me to specify for each axis a range that I want to process. Now, if I just have the column there, that just means all the rows. So this means all the rows, all the columns, which simply means the entire image. Right? And how the slicing works, I can specify a start value, a stop value, and I can also specify an increment. Now, the increment is useful if you want to, for example, subsample an image. If you have a very big image and you want to process every 8th pixel, every 4th pixel to speed up your algorithm, then you can just go there and say 450 to 600 colon 2 will give you every second row, right? Every 4th row, every 8th row, every 3rd row with an extra colon. So here we have the pixel value. The 3rd column is the 3rd dimension of our array, is our pixel, which is a 3-byte value. And I want to take the entire bytes, so all of them from start to finish, and my index should be -1, which means I start with the last one, then the second one, then the third one. So that's how it reverses the byte there. That's why you can do that in one line in NumPy. The slicing syntax is extremely powerful. Also, it has the huge advantage that it's implemented in C++. The NumPy functions, like all of this is running as C++ code, not as Python code. So it runs sufficiently faster, plus it's optimized for array processing, which means it includes the SIMD instructions, vectorization, and parallel processing. So on that entire image, basically your whole processor is going to town and processing it. So this is going to be also about 20, 30 times faster than writing a loop in Python to try and do that. So if you can, you want to make use of the NumPy syntax because it's vastly more efficient, much faster, much less memory than running the same thing as Python code. So now the color is correct. Now I just switched the red and the blue check. So now the boxes are brown or reddish. Now we can do some more fun with color channels. So I wrote a program that extracts the entire image, colon, and then the 0th byte, the first byte, and the second byte. So this will give me red, this will give me green, and this will give me blue. And we'll look at those 3 channels as grayscale images then. Right? There won't be any color information. We're just using the grayscale values. So it'll be just black to white. And then I'm plotting them in a Matplotlib figure. Now, one thing to keep in mind is if you're trying to do this, you need to tell it what color map to use. Because the value at this point is just 0 to 255, but Matplotlib has many different ways of assigning colors to pixel values. So one of the ones that we want to use in this case is we want to use it as a grayscale. If you don't do this, then you get an interesting color mapping. I think it's rereduced by default or something. I forgot exactly what the color is. But then you get like a false color. So these ones are useful too sometimes if you want to show colorized version of differences and things like that. But if you want it as a grayscale image, then this is what you need to specify the color. So here we have red, green, and blue channels now. So now I wrote a function which allows me to, maybe I shouldn't call it map, maybe I can call it. For reasons that will become apparent in a minute, I wrote a function to compress a plane. So what it does is for an image, a particular color, red, green, or blue, and then I can pass in a compression value. Now what that does is it extracts the plane, so the red, green, or blue channel, calculates the max and the minimum of that channel, and the average, and then it will replace that plane by subtracting the average. Should I write it like this? So I simply want to write it like that. So I take the difference of the plane minus the average, so that's over the entire image, and then I divide it by the compression. So that means that if my range before was from 0 to 255, and the average was 128, if I compress it by a factor of 2, then the average is going to remain at 128, but it's only going, the maximum and minimum value are going to be from 64 to 192. Right? So that means the range of that image is going to be compressed. If I tune up the compression, if I keep increasing the compression, what will happen is that eventually the whole plane is going to be just the average color, completely flat, no more high or low. And then I just write it back into the image. How come I have two? And for each image now, I just compress one of the planes by a factor of 2. And then we show what the resulting image looks like. Now you can see that these are the individual channels. So let's do that on our image. So before, the red plane was from a minimum of 0 to 255. So it was the entire range. and the average was about 128, and afterwards it's 192 to 64. It's sort of exactly the example that I have. The brain one, 0 to 255, 0 to 255. How come they go all over? Okay, so we'll see. And then here's the output. And so what can we recognize looking at the color composition here? So composed image 0 is the red channel is compressed, red channel compressed, green channel compressed, blue channel compressed. And the one thing that's apparent is which one has the biggest impact? The what? The brightness, the brightness is actually not changed, right? The average of the average brightness remains the same. Okay. So here we're looking at the changes in the color to the original image. So the original image looked like this here. And if we now compare it, then green definitely has the biggest impact. Right? The colors all look wrong there. Red, also, you can see some color changes. The blue one looks pretty good. Not that much change, actually. So now I can try that, and instead of compressing it by a factor of 2, I now compress it by a factor of 400. Now, that basically means that I simply replace the thing with the average brightness. So it's basically like throwing away the entire green, red, or blue channel. So let's see what happens. So you can see now, afterwards, beginning is from 0 to 255 for the red channel, right? After compression, it's from 124.5 to 123.9, which means that when we convert it to bytes, it's going to be the same integer value. The average, however, is not changed much, and then we can look at the impact on the colors here. And now you can clearly see that green now, you can definitely tell this has been manipulated. This is never the original color, right? And also the red one is clearly wrong, right? The boxes are, for one thing, now all completely wrong. And the blue one is still pretty okay. So what does that actually mean? That means that our eyes are very sensitive to green. And I think that makes sense from an evolutionary point of view. We'd be running through the forest, so we need to be able to understand what the different shades of green are from poisonous plants to not poisonous plants. And in fact, in nature, blue is not very common at all as far as like objects are concerned that they care about. The ocean and the sky are blue, right? But I think that's not something that you need, that blue is not something that you need to react to, right? So, but animals, plants, that kind of thing is not, there's not much in blue. And in fact, I'm not an art historian, but it's kind of an interesting story how some of the paintings, before they could actually make proper blue, like there was an arms race between different painters that were trying to get the pigments in order to make blue. So I think it's the Vermeer blue, isn't it? I think Vermeer is one of the Dutch painters who was famous for his blues. And nobody would he would never tell, like he would die before he would tell anybody how he made his blues. Because no other painter in the world could paint blues like he did. This is just about the letter. Um, so optical illusions, our vision system is extremely good, extremely sensitive, taking an image, constructing a world model from it. Computers are much worse than even young children. And in order to be able to do that, your brain has to basically take shortcuts. It has to take, of all the possible worlds that this could be describing, it has to pick the one that makes sense, right? Or is the most likely scenario. And if that is not true, then you can get things like optical illusions, right? Where this shortcutting of the brain simply does not allow you to see that the two squares are the same color. And sometimes you probably have experienced that effect as well. Um, when you walk down the street or you drive a car or a motor scooter, then sometimes in the edge of your vision usually, sometimes you have scenes that look like something else, like you see a cow or something, right? Because a couple of black blotches in the environment just happen to look like a cow. But then when you look at it, it's like a jarring experience, and your brain already intercepts it saying there's no way that there is a cow on the motorway at this position. Right? So then there's sort of a conflict between your visual cortex and your brain in what's a possible reasonable world explanation or interpretation of the image, a reasonable world model. And we looked at two of the optical illusions already that I like, pretty cool. Now, as far as the blue blindness is concerned, I think that's an interesting evolutionary trait of humans. When you look at the hardware in your eyes, the rods and the cones that allow you to, I think it's the rods that detect color, those are finely attuned to green, which is why we can see that much better. Now, there's a couple of reasons how this knowledge is being exploited. For one thing, if you want to convert an image from color to black and white, then how would you do that? If you want to convert an image from color to grayscale. The average, right? Red plus green plus blue divided by 3. You can do that, and it's fine for your robots, but it doesn't match how humans perceive lightness. So if you look up the exact formula, then it is actually 0. So if you take the average, then it would be 1/3 red plus 1/3 green plus 1/3 blue. That's the same way as writing the average, right? So the weighting would be the same on the red, the green, and the blue channel. But if you want to follow this, the way that humans perceive color, then it is actually 0.299 something multiplied by red plus 0.59 multiplied by green plus 0.11 multiplied by blue. Which means that the blue has much less weight when it comes to perception. About 5 times less than the green channel. And that can be exploited in various different ways. Of course, many researchers know this. So, for example, the JPEG standard. JPEG takes an image and compresses it, but it's a lossy compression, right? So the source and the decompressed image are not exactly the same anymore. In order to compress the image more, usually if you have an image and you're trying to compress it in a lossless way, then there's not much you can do. Because if it's an artificial image, you can do run length encoding and things like that. But if it's a natural image, one idea would be to say, okay, if I want to take this image and compress it, then I take all the green and I just replace it with the green, and then I just need 1 pixel with that green, and then I just say fill it with this, right? Fill this area. But the problem is when you look at it in a natural scene, these are not all the same brightness. They're not all the same pixels, right? Some are in the light, some are in the shadow. So run length encoding doesn't work on natural scenes very well because the pixels are all similar but all slightly different values. Then what other ideas would you have for compression of images? Another idea that you may come up with is, well, okay, this is all the same green sort of, but not exactly the same. So maybe instead of having 8 bits per value, right, 8 bits per pixel or 24 bits per pixel, I just calculate the difference from the left neighbor. And if the difference is, if the maximum difference to the left neighbor is maximum of 16, then I only need 4 bits instead of 24 bits to represent that. So then I could compress the image. All those approaches that would allow you to do lossless compression don't work particularly well in reality, so you can compress the image by like 20% or something like that. If you want to have real more useful compression, then you need to move to a lossy compression, like, and JPEG was the first one that did that, right? So how does JPEG get away with compressing an image that is 4,000 by 8,000 pixels and then compress it to 8 kilobytes or something like that? That's an enormous compression factor, right? Much bigger than what you could get using a lossless format. One of the ways that the JPEG compression works is it basically throws away the blue channel. It doesn't throw it completely away like I did, just 1 byte for the entire blue thing, but it subsamples blue by a factor of 4. So every 4th pixel is only checked for the blue pixel value. The other ones, the blues are ignored and then just filled in. Your brain does not see the difference. The green channel it's converted into brightness value, which is mostly the green component. That's compressed much less. So that's converted using a discrete Fourier cosine transform into basically kind of a frequency response over the image. That is then how the rest of it works. And I use that fact also quite often because when you do, like I said, in processing for our robots, what we want to do is look at shapes and things like that. So that means I'm not really interested, at the first processing step, I'm not really interested in the color. Most of the time for our processing, we try and not use color in the first couple of steps in our pipeline. Which then allows us to be fairly sure about what things are, and then we can have a much wider color predicate when we actually try and process the image. So when I have to do a conversion from color into grayscale, then one way to do would be the proper conversion based on the human visual cortex, which means I would have to do a bunch of floating point multiplications, which on a workstation CPU is not a problem. That runs fast, can be vectorized and everything. If you have a low-powered microcontroller, then that's, of course, a much more expensive operation. Then you can say, well, that's, of course, very expensive, so then I could calculate the average, but even that is often too much work. My favorite, or the way that I usually convert from color to grayscale is I just take the green channel. Because that's close enough to what you're going to get in most images. Unless you have an image where you have to do CSI crime investigator, you have to look all the blood splatter or something like that, then you need to look for red. You probably have to be a little bit more precise. But in general, you can get away with just taking the green channel, and it's just fine for our robots, have to understand. And of course, talking about CSI, this will be the final exam in the course, just to prepare you. This one, no, okay, that's a different one. There's a whole bunch of them. But so this is how that works, right? Just zoom in. Yeah, you're gonna have a fancy cursor that you can choose. Yeah. Yeah, according to CSI, this is possible. Just a couple of enhancement steps, and you get to read out that new Vitas, whatever that is. Oh, I know. And there's another one where they have a guy in the thing with the basketball that's even more absurd. And I guess since this comes up when you look for this, this is the latest deep learning by Google, right? So you can do things, you can enhance things like that. So you can pass in an 8x8 input and then generate a 32 by 32 sample, which is pretty close to the ground truth, right? But that is not what the CSI team said. This image here is a hallucination by the computer. That's not what, you cannot convict somebody because, oh, yeah, I know her. That was just because somebody looked similar in the training data. The actual image that would have resulted in this 8x8 image could have been totally different, right? So, yeah, these are if they use CSI in that format, then lots of innocent people are going to go to jail. Yeah, that's her. If you look too close to the training data, then you have no hope. You'll be convicted for lots of crimes. Your only hope is that you are sufficiently different from the training data. Good. So then, let us. Okay, so let's have a look at another image. So here's another example image. I should change that. Here's another example image for an impossible application where, let's say, you need to implement an algorithm to check the number of birds, singing birds in your neighborhood. Now, that is actually a serious problem and a serious research project. The number of singing birds is decreasing worldwide. One of the reasons for that, there are several reasons for it, of course, but the biggest threat to small birds in most places nowadays is why are there less and less birds? Pardon? Destroying the habitats, yes. Environmental factors, global warming, that certainly are important. But another bigger problem, bigger threat, are actually feral cats, because there's more and more cats. And cats are very efficient killers of small rodents and birds. In fact, New Zealand, when I lived in New Zealand has very special birds because it's been evolutionary sort of cut off. So it has a very special plants, special flora, and also special fauna. So they're very protective of these birds, and they found out that, and New Zealand is a small country, it's not a heavily industrialized country. They don't have a huge coal plant in Taichung. Of course, that's not good for the bird population and the human population either, right? Or enormous factory towns in China or India or places like that. But even they had a huge decrease in the bird population, and they were very concerned because those birds only exist in New Zealand. And then they figured out it was actually the cats that were the problem. So one of the environmentalists, he actually made a cookbook, and in the cookbook he said his favorite recipe was this one dish, and the reason why it was his favorite was because it used cat's liver, so you had to kill 4 cats to make one dish for a human. So he thought that that was a good start. And of course, there was a lot of backlash from people that actually like cats. But yes, so cats are a threat for small birds and rodents now. So when I was in Germany on sabbatical last year, they actually have the bird counting days. So there's a weekend in all over Germany, and then the citizen scientists, so anybody can sign up for it, and then your job is to go to a tree in the park there somewhere and sit there for 2 hours and count how many birds are there in that tree. Right? Because otherwise, the scientists really wouldn't know. Right? This is quite a huge data collection effort. And you had to, I'm not exactly sure how it worked, but there was a difference between the bird flying there and then sort of flying around, landing. If it's the same bird, you couldn't count it twice. But if it flew out of view and then came back, then you wouldn't, then you may count it as 2 birds. Because otherwise it'd be like pretty hard if you need to track all of these birds. So let's say you're a computer scientist or a roboticist, and you say, I'm not going to sit outside in the park for 2 hours. It's way too much sunlight. Who knows what's going to happen to me there? I want to be in the basement. League of Legends came out with a new version or something like that. So you decide to implement the computer algorithm to do the counting for you. And then, how would you approach that problem? So pretty simple, right? You point your camera at a tree, and then you just need to check how many bird-like things are in that tree. Mathematically, no problem. You need a function that, given a region, will return true or false, whether this is a tree or not. Yeah, I mean, you may get an inkling about why that this is actually quite difficult, because that's the kind of question they ask you when you need to solve CAPTCHAs, right? There's a couple of new ones now. They ask you, click on the elephant in the image. Click on it. So clearly looking at shapes and things is a good idea, and that's what we may do later on. But as a first attempt, you may go, okay, I'm only counting these kind of birds, so I'm just looking for the blue chest, right? That seems, so I guess that picture disproves my theory that there's not a lot of blue things in nature. But these birds are definitely in a blue chest. So, okay, I just find the blue chest, group it into one region, right? And then count it as 1. Then I can count the number of birds. Because shape-wise, I mean, there's a lot of variation, right? The sizes of these are different, whether they turn their head, the beak, whether they carry something in their beak, that's all pretty difficult. The blue part, of course, is not foolproof, because that bird here who's turned around, you don't have much blue to latch onto there. But you may think, okay, well, maybe I get something small. If it's too small, it's not a bird, I'll throw it away. But if there's enough blue pixels, then I count it as a bird. And this is what we want to implement. So I'm just going to run through the code that I wrote for this using Python and OpenCV. So here's just a function to be able to draw axis-aligned bounding box, a rectangle that is axis-aligned. Now we can look at the picture. And I picked out some region that I want to use as And I think I used this chest here. I know which one I used. So I just take this region and I say, okay, this is kind of the blue that I'm looking for. So all the pixels within that area definitely belong to the blue color predicate. And then let's see how that works. So here I can extract that seed now very easily using the indexing on NumPy arrays for minimums and maximums for the red and the green. So now I look for the minimum red and the minimum maximum, the maximum red in that region, right? And the minimum green, the maximum green in that region, and the minimum blue and the maximum blue in that region. Then anything that falls within that range for the red, the green, and the blue channel is considered to be blue, corresponding to the chest of the bird. And then we can color it in. And I just count. So for that image, we have 90,407 pixels that were detected as blue. And then I can show it. And then here's our result. So actually, when you look at it, you think, oh, actually it's not too bad, right? We colored in most of the chests pretty well. We have two types of errors, two areas that are problematic. Here, we're missing part of the chest, so this would be a false negative. Right? The algorithm says this doesn't belong to the chest, but actually it does. Here, these would be true positives, because the algorithm says it's a chest, and it is actually a chest. Okay. Here we have a false negative. Here, we have lots of false positives, where the algorithm says this belongs to the bird, this is a bird, but actually it's not. And then the entire background here, all that yellow and green, those would be true negatives, where the algorithm says this is not a chest, and indeed it is not a chest. Now, one of the most important realizations in computer vision is that we can tune the algorithm. There's lots of parameters that our algorithms have. So if you want to include a particular feature, there are many knobs you can turn, right? But whatever parameters you change, they will have an impact on your error rate, and usually it's sort of a trade-off. If I want to get rid of those false positives, right, then I need to squash the color range that I allow for the blue chest. Right? If I do that, I will also get more false negatives here. So I can reduce the number of false positives, but if I do that, I have to take into consideration, most likely I will get more false negatives. If I reduce the false negatives, which means I would include this area here, we'll do that later, then I will get more pixels that are classified as the chest, so I will get more false negatives at that point. To find an algorithm that is 100% accurate, which means your false positive and your false negative rate is 0 is basically impossible. No hope of achieving that goal. So all you can do is balance off the false positives versus the false negatives. The other important realization is that the impact of false positives and false negatives is usually very different, or it may be very different. There's lots of applications where a false positive will may have a very detrimental effect, or it may not have such a detrimental effect. This is not just true for computer vision, but it's true for any kind of classifier, any kind of machine learning algorithm that you implement in order to make a classification. So label something as belonging to class A or to class B. Anytime you're trying to do that, then you have to be concerned about your false positive and your false negative errors. For example, you want to implement a vision system or a machine learning system that looks at ship engines, right? That was one project that we did. Now, ship engines are enormously big. Ships are big, the engines in there are huge, right? They need to be maintained, because otherwise your conveyor ship is going to be stuck in the middle of the ocean with no power to go anywhere. Right? Or engines in an airplane, similar to that. And they have certain periodic maintenance schedules that they follow, of course. But sometimes some engines develop a problem, and if the engine if you think it's broken, then you need to take it out of the ship, costs a lot of money to repair it, refurbish it. So in this case, then let's say your false positives would be, you say the engine is broken, right? They take it out of the ship, they refurbish it, and the guy says, no, there was nothing wrong with it. Right? So you said it's broken, but in reality it was not broken. And your false negative rate would be, you say, no, that engine is fine. The ship goes out, middle of the Indian Ocean, all of a sudden, no more power. Then they need to send out tugs to pull you back into harbor. If it's a plane, you may have just killed a couple of hundred people. So in this case, your false positive, false negative trade-off is very clear that it's better, much better, to have a couple of engines where you waste money to have them refurbished, even though they didn't need to, right? As opposed to having any false negatives. So in this case, you want your algorithm to have a higher, you have to accept that your algorithm will have a higher false positive rate if you want to make sure that you don't have any false negatives, or as few not false negatives as possible. And that is crucially important. Now, this is just the very basic level of classifier. There's a whole theory behind it for classifiers. You can calculate F-scores, which is a special mathematical formula to weighing false positives, false negatives, true positives, true negatives. You can calculate confusion matrices. You can calculate the receiver operating curves. Those are all advanced techniques to try and find the right parameter setting for your application to match your trade-offs. But the most important thing is not to apply those techniques, to just understand that this is a huge problem. That it's impossible to come up with the optimal algorithm. Now, I would like to stop there today. You should implement your own color detector. You can either do it manually like I did in my Python code, which just checks the color predicate. Right? It takes the image and takes the red, green, and blue channels, pixel values, and then checks is red less than or equal to the minimum threshold, greater than or equal to the minimum, and less than or equal to the maximum. And green is greater than or equal to the minimum and less than or equal to the maximum, so on and so forth. Right? Or you can do the in-between. OpenCV has a function that does that much more efficiently, which is the in-between function that you can specify the two thresholds and will do that for the whole image much faster. And now for the rest of the class, another 30 minutes, you should try and implement that yourself. I actually have an idea that I wanted to try and do. OpenCV is actually not that easy to install if you want to have it run as an application on Android or iPhone or things like that. So the one technology that I find pretty interesting at the moment is the WebASM stack, which allows you to take programming languages like C++ and Rust and convert it into WebAssembly, which runs in your browser. It's basically a virtual machine for the JavaScript engine, the V8 engine. And you may have heard of ROS, right? The robot operating system, for example. That's very popular for developing AI application for robots. But the move from ROS 1 to ROS 2 is going very slowly. There's lots of packages that are not ported yet to ROS 2. There's lots of device drivers that are not supported anymore for ROS. And the reason for that is that the robot operating system is now driven by volunteers and professionals, like hired developers, from the Open Source Robotics Foundation, or OSRF, right? So I know the OSRF guys. I think on Gazebo, for example, there's 4 developers working on that from OSRF, plus the community of people supporting it. If you compare that, so that's why Gazebo is not really such a nice simulator to use. Right? It gets the job done, but it is difficult to set up. ROS itself, anything but past Ubuntu 18 is already a huge nightmare to get it set up. If you think about the number of people, developers that are hired by Microsoft, Google, Mozilla, Opera, and so on, that are actually working on improving the JavaScript engine, then this is thousands of people. Right? And every aspect of that engine is being developed further and further. So I kind of do a lot of development now using the V8 JavaScript engine, using WebASM. And that makes it then a lot easier to run things like OpenCV on an Android phone, because actually you will just serve it as a web page. So I just want to try and see if this works under the Google Collaboratory. So you can implement a program, capture images from your camera, and then implement a simple color predicate like this. So do that, basically what I did with the birds, except do it for a live image stream. And at the same time, I'll see if I can get this to work on the collaborator. That will be kind of interesting. In fact, OpenCV on Android and iPhone, if you want to have it truly cross-platform, it's not easy. So I failed to do that a couple of times when I tried it. So I actually came up with the idea of instead of implementing, trying to port OpenCV to a new architecture, which is not so easy, not working so well. What is supported pretty well by all the iPhone, Android, Mac OS, Linux, and Windows, of course, is the networking stack, because that's very popular right now. So TensorFlow and PyTorch is much easier to port than OpenCV. Right? If you tried it yourself, then you will realize that you don't need to worry about different versions of this library and that library and incompatibilities like that. So I actually, as a joke, I thought I'm not going to write OpenCV at all anymore. I'm just going to write everything as a neural network. And if I want to have an OpenCV program, I'll write the OpenCV in Python. Then I generate random images, and then I show the output of my OpenCV program. I'll feed that as a training data to my network, and then I'll just run the network when I actually need to do the processing. That, of course, doesn't work because the amount of training data that you may need in order to do a face, that would work for things like edge detection. You can probably do that, but face detection or something more complex, you would need to generate the right kind of training data, because otherwise it's just going to say no face, no face, no face, right? Because if I generate random pixels, the probability that I have something that looks like a face would be zero. So that was just I just said that as a joke, but it certainly would make the porting easier. So now let me see what I can do here, and you guys should also open and start writing your own image capture for OpenCV, and then simple color predicate that you can pass it. And you have 20 minutes to do that. So first I need to serve some HTML. Okay, so first, let me find out how to do. Okay, so let's try first if we can actually do a simple HTML page. So 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 this looks a little bit different from Python, but the semantics are very similar. Alright, and what are the arguments? And yeah, I just want to make sure I can actually find some JavaScript because Google disallows a lot of things. Oh, okay. Yeah, yeah, yeah. Sure. Yeah, yeah. Yeah, if you're done with your program, you can leave. Open CD. Uh, see what Google says. Okay. Uh, yes, so Google collaboratory blocks localhost. And I've tried this before. But you can run it in a normal root. I think that will work. Okay, good. Then that's it for today. Unfortunately, that doesn't work with Google Collaborate. So this is all. Okay, so let me try something else. Correct? Yep. That's what you should have been doing for the last 30 minutes. Yeah, but you can mark anything else you want with colors. Like it doesn't have to be the blue birds. If you don't like birds, you can do chairs, red chairs, or leaves on a tree or green or something like that.
Try to detect and mark.
Correct, yeah. Just detect colors and mark them. Okay, yes, that's exactly what we want. And then we'll bring in a couple of colored objects next class. And then you can see how difficult it is to or track a tennis ball on the field. Okay, good. Yes, very nice. And by the way, next class, Wednesday, will be a virtual class, but I'm not sure if the meeting will last too long, then I may have to cancel the class. But definitely will not be in person, because I'll be Italian.